Alright, this is just continuation of the logarithm stuff. So let's go and find a good example here. This example is a little bit more complicated than what you just did. This time you're actually going to solve for x. Look what they tell you. They tell you this number and they tell you this number right here, and they ask you to solve for the base. Now, the way it's written right now, I mean, do you know anything about logarithms right now? Not really. The only thing you know about logarithms is how to do what? Change it from a logarithm to a what? To an exponential, right? Okay, that's the only thing you know right now as far as logarithms are concerned. We're going to learn some more things, but right now that's the only thing you know. So that's really your only choice right now is to change this into an exponential function. So let's do that. So if it's a logarithm, what do I go for first? The base, right? So I write it x to the certain power. To the third power, good. To the third power. Remember, that number that's sitting there by itself is always your exponent. So you take the base to the power. Notice what you're doing? You're going from one side to the other, aren't you? You're going the base to the power equals the number. All right, we'll call that the number. Is that all right? So you go base to your exponent, to your power, equals the number. And so that equals what? 8 over 27. So now you can actually solve for this. You say, no, I can't. Well, sure you can. Look at it. Just think about it a second. We got to get x by itself, right? So how do you get x by itself if it's being cubed? What do you think? What's that? Cube root. Very good. Okay, let's take the cube root of it, right? That's the inverse of cubing something. It's the opposite of cubing something. It's taking the cube root. So if I take the cube root of the left side, you know it's going to cancel out. Well, what do I have to do over here? I got to take the cube root of the other side as well, don't I? Now, did you notice that they rigged this? All right, because you can take the cube root of both of those numbers and it comes out to a nice whole number. So they do that on purpose to make life a little easier for you. So what's the cube root of 8? It's 2. And what's the cube root of 27? It's 3. And that's your answer right there. That's kind of weird to have. It's kind of weird to have a base of 2/3, but that's what it would be. All right? Does that make any sense? So now do you see how valuable it is changing it from one to the other? Yeah. Now there will be some times. Now it looks like the only real benefit is changing it from a logarithmic function to an exponential function. And people are probably thinking, well, why even start with a logarithmic function? Why don't you just start with an exponential to begin with? Because I can solve for that. But again, there are reasons for that. You're going to learn here in a few minutes. Some good reasons to use logarithms. But this is all we're doing. Is just going from one to the other, one to the other. Let's try another one. Let's do this one. What if I do log base 4 of x equals 5 halves? 5 over 2. Alright? So there we go. That's in logarithmic form again. But I don't want to have it in logarithmic, if I could talk right. I don't want it in logarithmic form because I don't really know how to do anything right now with logarithmic form. We're going to learn that a little bit, but right now we don't know anything about it. So I'm going to change this from logarithmic form to exponential form. So again, let's do the same thing. This is like the 4th time today we've done this. Okay, we've changed it from logarithmic to exponential. What do we start with again? The base, which is 4. So we take 4 to which power? To the 5 halves power, right? It goes 4 to the 5 halves equals the number. And what's our number here? It's x. So it's 4 to the 5 halves power equals x. And all we have to do is simplify this. And we do need to simplify it because it does simplify. I don't want to leave it 4 to the 5 halves. Again, they've rigged this again for us. Because we did one of these yesterday. And we've done this in the past this year as well. We're going to break this up. Not into the 5 over 2 power, but we're going to go 4 to the what first? To the 1/2. Okay, always go 4 to the 1 over the denominator, then take that and take it to which power? To the 5th. Good. And that's what it's going to equal x. And that actually makes things a lot easier for us, doesn't it? Because what is 4 to the 1/2? It's 2. And it's not because it's half of 4. What is it? It's the square root of 4, right? So the square root of 4 is 2, and now we just go 2 to the 5th. And 2 to the 5th, if you do the math on that, is 32. And so that's your answer right there. So log base 4 of 32 is equal to 5 halves. Now again, that might not make any sense to you at all as far as log base 4. What does it mean to be a base 4 and all that kind of stuff? But we're going to learn a little rule here. I think I'm going out of order a little bit, but that's okay. I think I'm going to skip right to this rule. And it looks like they don't even do this rule in this lesson. It looks like they probably, yep, they do this rule in the next lesson. But I think this is a perfect time to show you the rule. And so let's do it right now, because it really can be very, very helpful. For instance, that example that I did earlier, like this one right here, okay? That rule right, or that problem right there, log base 3 of 81. Again, this was pretty much rigged, all right? I rigged it myself, so it came out to a nice whole number, all right? Because look, I can do this. I can go 3 to the x is 81. Okay, I can write 81 with the same base and all that kind of stuff. That was rigged for me. Sometimes they're not always going to be that rigged, and there's sometimes the only way you can do this is if you use your calculator, all right? You know what? Now that I'm thinking about it, yeah, let me just show you how to do the rule, and we'll talk about it. When we get to that next lesson, we'll talk a little bit more about it, because I'm kind of leaving something out, but I'll just show you how to do it. I'm not going to really give you an explanation of that. I'll just show you how to do it, all right? You okay with that? So here's the rule. It's called the change of base. It's called the change of base theorem. Again, I'm not going to go into a lot of details on this just right now. Now, we've seen several different bases, but your calculator actually has a logarithm button on here. Did you notice that? Where is it? Right there. LOG. Do you see it? For log. Now, this button down here, it's got an LN. That's actually a logarithm button as well. These are actually two logarithms with bases, with two different bases pre-programmed into the calculator. So I can't really put something, if I had like a log base 3 of something, I can't just take that and stick that into a calculator and say, oh, log base 3. You have to know this theorem to be able to put it into your calculator. The calculator is only programmed with two bases in it, and one of them is not base 3, okay? There's two bases. There's log base 10. Again, I'm not going to get into a lot of detail on this, but you also have log base E. You think of base E, what in the world is that? Again, we'll talk about that later, but E is actually a number, kind of like pi. It's an irrational number. You know how pi is 3.14159, blah, 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 and it keeps on going? Well, E is the same type of number like that. It's an irrational number. It keeps on going. It doesn't repeat itself. But just realize that that's a number, all right? So whenever you see the log base 10 on your calculator, it's just written as log. It doesn't say base 10 on your calculator. This is called a common logarithm. Okay, it's called a common logarithm. This is called a natural logarithm. And I'm skipping a lot of stuff here, but just enough to give you the idea of how to do this change of base theorem. You could actually use either one of these. You could use the natural log, or you can use the common log. And on your calculator, the log base E looks like this. Looks like ln. All right, and that's what that ln on your calculator is. That's the natural log. See that ln right there? They're capital letters, but that's what that is. It's the natural log. Again, let's not worry too much about that right now. Let's just do this change of base theorem. Here's what it says. It says if you have log with a certain base of a number, right? So this is like log base 7 of 23 or something like that. You can actually do that in your calculator, even though your calculator does not have log base 7 programmed into your calculator. There's really no buttons you can push to figure out what log base 7 is on your calculator. So you need to know this theorem that we're going to do right here. And it's actually very, very simple. Watch this. You're going to do this. You're going to go log of x. Now watch. If I don't have a base, if it doesn't say a base at all, guess what base it's assuming? It's assuming base 10. And you can actually do base 10 on your calculator. So when you don't see a base here, if it just says log of a number or log of x, you can assume, you can say, and it's really not an assumption, they're telling you, if you don't see a base, it's going to be log base 10. Everybody understand that? So you can actually put that in your calculator. So what we're going to do, we're going to go log of x over log of a. That's your change of base theorem. May not look that great right there, but it's really, really beneficial to us. You say, how does that work? Well, I'll show you. I'm just going to make some numbers up. What did we say before? We said like log base 7 of let's do this. Let's go like a 51. All right. Everybody watching? So log base 7 of 51. Now watch. If I wanted to do this, changing it to exponential form, I'd run into a little bit of a problem. Let's see where the problem lies. What would I write? I'd write, if I was going to change this to exponential form, what would I start with? The base. All right, so I'd start with the base, and I'd take it to which exponent? X, and that should equal what? 51. Now, I got to think of a number. 7 to what number is going to give me 51? Well, I could come pretty close. What's kind of close to 51 that has a base of 7? 7 what is kind of close to 51, wasn't it? 7 squared, right. 7 to the second, right? 7 squared is what? It's 49. So what do you think this x is going to be? It's not going to be exactly 2, is it? Because if this was a 49, then x would be exactly 2. So it's going to be what? What do you think? Just guess. 2 what? 2 points. You think it's going to be 5? You think it's going to be that big? Probably something really small, I would think. 2 point something probably small. I would probably guess 2.1. That would be my guess. And I have no idea. I just made this number off the top of my head, okay? So how in the world can we do that in a calculator? Well, we could sit there and go 7 to the 2.1. Let's see what that's equal to. Let's try that. All right. Watch. 7 to the, what do we say? 2.1. Let's see what that is. Oh, that's all the way to 59 to the 2.1. So what do you think x is going to be? Probably a lot smaller than that, right? So let's try another one. 7 to the 2 point what? How about 0.1? Let's see what that does, right? Oh, that's a little too small, isn't it? You see what we can do? We could sit here going all day trying different numbers to see what x is equal to. Would you agree? Let's try another one. Let's try like 2.05. Yeah, so it's, what is it? 7 to the 2.05. Oops. Let's try that again. 7 to the 2.05. Right? So that should be a little bit closer to 51. Oh, still too big, isn't it? So let's go like 7 to the what? 2.03, let's say. Ah, we're getting a little closer, 51.9. You follow what I'm doing here? I could sit here doing that all day, couldn't I? Until I get really, really, really close to 51. But you get the general idea. I don't want to sit here and do that all day. What I need is another way to do this, and that's what this thing right here is going to do for us. It's going to get us right on. It's going to get us, not exactly because the decimal keeps going, but really, really close to this. So how do we do this? Use the change of base theorem. Look, what's the x in this case? So this is this, isn't it? All right. So what am I going to do? I'm going to put log of what? No. What is the x here? Is the x where the 7 is? What's on this one right here? What's in the place of the x? It's 51, isn't it? Do you see that? I'm just going by that little formula right here. This says log base a of x equals log of x. Which one is the x? It's this one. So it's going to be log what? 51. Over what? Log of a. What's the a on this one? It's the 7. Now again, these are log base 10, so I can do this on a calculator. So I just use the log button on my calculator. So let's do this. Watch. Log of 51. Now in this calculator, I hit the log first, then I hit 51. If you have one of the smaller, just little scientific calculators, you would hit 51 first, then you'd hit log. All right, so on this one, I hit log of 51, and then I divide it by, what do you think? Log of 7. See that? And watch what I get. Bang. Look at that. Isn't that real close to the number we thought it was going to be? Remember we tried 2.03, it was a little bit big. We're going to try a little smaller and on and on. So that's what it would be. We'll say about 2.02. We'll round it. So that's going to be about 2.02. Approximately. It's a little squiggle right there. Okay, it's not exactly, but it's approximately. And that's how you use the change of base theorem. It's actually pretty easy. And it should make sense to you, right? Because when we did this and we stuck a bunch of numbers in for the calculator, we came pretty close to 2.02, didn't we? Right? We said it's a little bit bigger than 2. 2.1 was way big, and then 2.01 was too small, and then we just tried some other ones. So it's 2.02, blah, blah, blah. All right? All right, that should be enough to get you going on this worksheet, and we will stop right there.